Hello, this is the second class of our series on the mathematics of data science and machine learning. In today's lesson, we are going to be picking up from where we left in our last class. In our last class, we covered matrices. So in today's lesson, we are going to be covering linear algebra. And linear algebra is more or less about matrices and their various transformations. Today's class is divided into two broad categories. The first part is going to cover matrices as storage units, and later on in the second class we are going to be covering matrices as transformations or operators. A matrix is simply an arrangement of data into rows and columns. One thing about matrices is that they are very naturally occurring, and one example I can give is spreadsheets. So a spreadsheet is simply an arrangement of data into columns and rows, or in short, tables. And the intersection between a row and a column in a spreadsheet is called a cell, and in a matrix equivalent we call it an element. So what are the different types of matrices? We have a row matrix and a column matrix. These are very similar, with the only difference being that a row matrix is horizontal in nature and a column matrix is vertical in nature. And a column matrix is particularly helpful when we are doing multiplication by another matrix. So we can take a matrix A, multiply it by another column matrix AX, and from there we get another entity that we can use for data manipulation or for whatever purpose that we may require to do. So what is an example of where we might use a column matrix? We can use a column matrix to denote weights, and with those weights we can multiply them by another matrix and build on top of that until you have something that we can work with. So there we have a square matrix. A square matrix simply has the same number of rows and columns, and it is more or less a general purpose kind of a matrix. A diagonal matrix simply has 0 elements except on its leading diagonal, where it has some entries. So we can see there a matrix has 2, 3, 5 as entries. An identity matrix can be seen as a diagonal matrix where the leading diagonal elements are just ones. Diagonal matrices have some very useful properties that we can use for data manipulation and operations. And one example of where we can use a diagonal matrix is in a process called principal component analysis. And this is a procedure that involves reducing the dimensions, or this is a process that involves condensing the information that we have on a matrix. Say we have a very large spreadsheet that consists of very many variables, say age, name, height, etc. We find that the data can be very noisy and it can have some very large variances. So PCA analysis comes in handy when we want to only get the more important features of our data. We shall cover this in great detail when we learn about neural networks, and especially when it comes to the first step of machine learning, and that is data analysis. We'll want to get a clearer picture of how our data looks like and which are the more dominant features in our data. So there we have a positive definite matrix. A positive definite matrix is simply a matrix that has positive eigenvalues. We can view eigenvalues and eigenvectors the same way we view prime decomposition of numbers. E.g., for the number 20, we can decompose it into 2 primes. So we have 2 squared times 5 and we get our number 20. So in the same way, we can decompose a matrix into its eigenvalues and its eigenvectors. So what are the applications of a positive definite matrix? Again, we can use the positive definite matrix in PCA analysis and in optimization problems. Then there we have a triangular matrix. A triangular matrix resembles what we previously defined, and that is, so we have the 0 elements either on top or below the diagonal, and that is how we essentially name triangular matrices. So we have a lower and an upper triangular matrix. So these kind of matrices are particularly important, especially when you have a positive definite matrix. You can decompose it into a lower triangular matrix and a conjugate transpose. So you can decompose a positive definite matrix into a lower triangular matrix and another matrix. So what is an orthogonal matrix? Orthogonality simply has to do with the right angles, and right angles are usually well behaved, especially when it comes to points and plotting. So where do you use orthogonal matrices? We use orthogonal matrices to curb the problem of vanishing and exploding gradients in neural networks, more so in recurrent neural networks which have these problems. So when we get into our neural networks class, we shall be looking into RNNs, i.e. recurrent neural networks, and some of the problems that they face and how we can combat them. And one of the ways that we shall be doing this is by using algorithms that mitigate exploding and vanishing gradients. So what is a Hermitian matrix? A Hermitian matrix is a matrix which is equal to its conjugate transpose. This kind of matrices are particularly useful in physics and some optimization problems in machine learning. Let's look at the applications of matrices. The first one is linear transformations. This one we shall be covering it in the second part of this course. Number 2 is solving linear equations. Matrices are very useful in the representation of graphs, nodes, and objects in general that have some kind of a relation between them. And when you start using TensorFlow, you are going to be hearing more about graph computation and other terms that have to do with graphs, on why graph computation is one of the reasons that TensorFlow is very efficient. And being one of the early adopters of graph computation, we can see why TensorFlow has an edge over other frameworks. The application of matrices is statistics and data analysis. So matrices are used to store data, and with that data we can perform various statistical operations, and with this we can be able to build machine learning algorithms like Bayesian methods and other statistical tools that we shall be using. So let's get into data storage. So let's define what a tensor is. A tensor is a mathematical object that generalizes the concept of scalars, vectors, and matrices to higher dimensions. So in this class really, or from this point forward, we can use the term tensor interchangeably with the term vector or array or similar terms that refer to a tensor. So there we have a one-dimensional array. A one-dimensional array is simply a list, and I simply borrowed our previous method to illustrate how an array looks. So one thing about lists is that Python has some very good methods that are built into the program, and you can use them for various operations. But for more powerful use cases, you will want to use libraries. One such library that we shall be using is numpy. And one thing about numpy is that you can convert your lists or your arrays into a numpy array. And there, as you can see there, I have an example where I declare an NP array, and in another example where I convert a list into a numpy array. So as you work with numpys or higher dimensions, that is more than one dimension, you're going to encounter one big problem, a problem when it comes to visualization. So for new students in this field, we find that one of the biggest problems that they face is how to visualize higher dimensions. So we use something called the tuple, and the tuple is used to define the shape of an array. So there we have a 2D array, another 3D array. So for the 2D is quite straightforward, and you can be able to see that it is a two-dimensional array. But for the 3D, it's not quite as obvious. You can pause and try guessing the shape of the 3D array. What did you get? So the shape of that array is a 3, 2, 3. So what do you think a 3 by 2 by 4 by 5 array looks like? So again, pause and think of how this array looks like. So there is the correct answer. One of the tricks that you can use to infer the shape of an array is to start inwards and then you go outwards. So in our example there, we can say that every list in the innermost dimension has 5 items. Then the next list has 4 lists with 5 items. So we do this iteratively until we get to the outer element, and that is 3. So there is the correct answer. I have rendered the shape of that array there. It has a random functionality that can assist you to generate random data as long as you give it the shape and the interval that you wish your elements to be generated from. And in my case, I chose 0 to 10, and there you have your 3 by 2 by 4 by 5 array, you can pause and be able to appreciate how intricate the array is. So in general, the shape of a nested list reflects the structure of the data, with each level of nesting representing an additional dimension and the length of each inner list determining the size of that dimension. So these are not very easy to cover, especially in a tutorial. So we shall dedicate an entire lesson to shapes, reshaping, and working with different dimensions. So another important skill that you need to have as a data scientist is writing SQL queries. So SQL is like the industry standard for relational databases, and being the industry standard, it means that a very big chunk of the data will be stored in a database, and sooner or later you might need to access this. You might need to know how to access the data in a database and to convert it into a form that you are more comfortable with. So there we have the process of converting SQL data into numpy arrays. So you connect to SQL DB, then you execute a query where you fetch the data, and then you transform the data into a friendly format that can be converted into NP arrays. Then from there you can decide whether to store it, to do operations on it, etc. So let's cover another very important data manipulation tool, and that is pandas. So if you love the numpy, then you're going to enjoy pandas. So pandas is a powerful Python library that is used for data manipulation and data analysis. So if you learn about numpys, you can easily cross over to data frames and other kind of pandas objects. So let's begin with the first one, which is a data frame. A data frame is a two-dimensional labeled data structure with columns of potentially different types of data. So there we have a simple data frame and some few operations. A series is a one-dimensional labeled array capable of holding data of any type. So there we have an illustration of how to create a series and the various operations that you can perform on a series. And then we have in addition we have more operations that you can do. We have indexing, selection, and some few data operations. So there we are dropping some values, we are filling some values, and we are also combining some data frames and merging them into one. At this point, I'm assuming that you have a general idea about numpys and pandas, and after familiarizing ourselves with the numpys, SQL, and pandas, we need to look at another crucial aspects of data analysis, and that is data persistence. So this is simply storage, to put it into layman terms. So what is the importance of data persistence? One is reproducibility, and that is being able to do something over and over again, or the ability to replicate something. Then you have collaboration. So if you visit some sites like Kaggle, you're going to find some very nice data sets, and these are very important when it comes to collaborations. So you need to know something about data storage so that you can collaborate more easily. The other aspect is scalability, and this goes hand in hand with what we talked about, the industry standards, especially when it comes to SQL. And one of the problems that we have in programming or in the DevOps or development is scalability. So you need to have a general idea of how you can scale your data set, or how you can build on top of what you already have, and be able to do more operations, to be able to work with larger data sets. So another important aspect is tracking. You need to know how your data evolves over time. So this will help you to avoid issues like duplication or erroneous deletion. So sometimes you can find that you're deleting data which is not specifically a duplicate. This can happen if you don't have a good way of tracking your data. So what are some of the common persistent techniques? One of them is using CSVs, JSON, and other formats. One of them is to use a file system. So a file system, you can use CSV, TXT, JSON, etc. Again, you might want to store your data in a server. It is very handy that you know how to work with databases and how to store your data. So another way you can store your data is in cloud. Yeah, this is quite straightforward. So what are some of the best practices that you can incorporate into your machine learning day-to-day operations? One of them is to choosing the right format. For instance, myself, I prefer using CSVs. Another is to focus on security. So security goes hand in hand with privacy. At one point, you shall be entrusted with private information, and you might want to do some encryption or store it in a safe environment. Another aspect is metadata management. This mostly has to do with the retrieval, and if you're going to do fast retrieval, you're going to have to write some very good code when it comes to metadata. So again, as we talked about version control, you're going to need to do monitoring and have alerts. So in this section, we are going to look at matrices as transformations. So in our first class, we defined matrices as some kind of operators, and in our previous class, we defined matrices as a special category of operators. You are very lucky today. We are going to be doing a very practical, hands-on approach that involves building a photo editing application. The application is quite elementary. It is not very complex, but it will show you that using matrices, you can do all the operations that you might need to perform when it comes to editing vectors, editing graphics, editing photos, videos, or any other kind of data that is in a graph-like kind of format. As you can see there, we have our Jupyter notebook, and inside that notebook we have some Python code. We are going to be using numpy to do the various matrix operations. So there we have Bob. Uh, Bob Bob has some two eyes, a nose, and some lines indicating his mouth. The next operation that we do is that we decompose the picture of Bob into pixels. As you can see there, we have a nested list which contains a line by line decomposition of the picture. Then we have some matrices there. The first matrix represent a 90 degrees rotation. We have another representing 180 degrees, another doing a flip. So what I want you to understand is that we are not only limited to using a 2 by 2 matrix. We can use other shapes to sort of do operations or to edit our picture depending on our desired effect. It's only that for the common tasks like rotation, shearing, mirroring, or flipping, we prefer using a 2 by 2 matrix because it's very easy and it maintains the original configuration of the elements. We have a function. The function receives a matrix and a face. So it's going to receive Bob's pixels and a matrix. So down there we have a rotation. So the rotation simply takes in the matrix and the face. The same case to all the others. And then down there we have our original face. We have the rotation by 90 degrees, which is not as obvious. Then we have a rotation by 180 degrees. This one is rotating each and every element in Bob's face. Then we have a horizontal flip. This is very accurate, as you can easily verify that indeed Bob's face is being flipped. Marching forward, we are going to introduce a very advanced concept called spectral theory. Spectral theory is simply the mathematics of decomposing a matrix into its eigenvalues and eigenvectors. Spectral decomposition is simply the decomposition of a matrix into a diagonal matrix and a matrix composed of its eigenvectors. And then with that matrix we can get the inverse. And then from there we kind of study the different properties that the matrix has. What are some of the applications of spectral theory in data science and AI? Again, since it involves diagonal matrices, it is very crucial in PCA analysis. It's also very important in clustering. You can be able to reduce a data set into clusters, and it will be easier to operate on. And then we have solving graph problems and NLPs. NLP is a natural language processing. So if you're working on a translation algorithm, you might incorporate some aspects of spectral theories, and spectral theory is also very important in quantum physics, and so by extension we have another branch of some computers are computers that are designed to solve certain problems, and so you can incorporate aspects of machine learning into quantum computing. So again, we can use spectral properties in transformation and AI models. And one thing I can challenge you, you can look into algorithms that use spectral properties, especially in image generation or in image editing or video editing. You can incorporate spectral properties even into your photo editing app. You can incorporate spectral properties into image generation. And one good thing is that remember that the goal of this entire process is to abstract. It is to abstract as much as possible. So if we can abstract up to the best limit that is allowed, you can get better results. So one of the ways that you can do this is by using spectral methods. So thank you very much for staying through to the end. And in the next lesson we are going to be covering calculus. So you can prepare, you can